Hampshire, England, the birthplace of flight in the UK. Home to one of the greatest aeronautical events on the planet, Farnborough International Air Show, where the biggest aerospace players unveil the world's most cutting-edge technologies.
This is gate B.
Can we be a bit gentle, Dan? I don't want the engines to fall out.
I'm not used to driving this.
But this year, an ambitious team of engineers are showcasing something so unique, it could steal the show.
So we're heading onto the runway.
Capable of making an impossible dream a reality.
Mankind has always had this passion for flight, always looked up at the sky and thought, gosh, I wish I could do, frankly, what the birds do.
An innovation that will allow man to fly free.
We've had a great history of putting human beings inside flight vehicles, helicopters and aeroplanes. I think there's something deeply inspiring about the process of slimming that down to that raw, kind of impossible point where you as an unencumbered human being could just float around and move about wherever you like.
The awe-inspiring solution, the personal jet suit.
The suit consists of 5 gas turbines. They're the same jet engines that you see on a jet aircraft. Together, they produce enough thrust that you could equate it to around 1,050 horsepower, about 1.3 times a Formula One car. In terms of straight line speed, we set the record at about 32 miles an hour. It's a Guinness World Record.
This infeasible engineering is the extraordinary vision of inventor and test pilot Richard Browning.
We have opened the doorway onto a whole new realm of human mobility that was previously just the domain of superheroes in the science fiction world.
Trailblazing design also shaped by aeronautical engineer Angelo Gruberzic.
With this simple, small amount of equipment, you can essentially gain that full three-dimensional control of human flight that people have been aiming for the last 100 years. And I think that's something that's very special.
Weighing just 45 kilos, the jet suit is made from aluminium alloy, nylon polymer and steel. Twin tanks holding 40 litres of jet fuel feed 4 microjet engines mounted on the arms and one on the back. All controlled by a fingertip throttle trigger and packed into just 2 flight cases. Minimal kit to turn man into flying machine. Richard and the team are using revolutionary technology. But now their jet suit is about to be put to the test in front of the movers and shakers of the aeronautical world.
Can you check I'm not twisted underneath there?
In a show where $170 billion of deals are struck each year.
So we're going to drive out to the edge at like 2 minutes to 1 or 3 minutes?
We're going to get going as soon as you're ready.
Oh, okay.
The team are keen to put on an impressive display.
This is something that people have not seen before, and many of the public are unaware that this is even possible.
Good, heads up working.
But with human flight, nothing is guaranteed.
I'll kick the back when I'm about to take off.
There's a potential of having an incident. You know, if one of these engines suddenly fails, you know, things can fail.
When you're building the impossible, the challenges are huge.
Okay, I'm good.
For a start, getting airborne at all means defying the laws of physics.
The human body is not designed to fly. We don't have any flight surfaces, we have no means of propulsion, we don't have wings, we don't have anything that actually lifts us.
So how do you launch a man into the skies?
You require a lot of power to produce enough thrust to get yourself off the ground.
And once airborne, how can you maneuver safely?
We honestly didn't have an idea of how we were going to do this, and it was a potential reason why this might be infeasible.
Today's flight is the culmination of 15 months' development. But to achieve the impossible and fly like a bird, the team have had to turn to the pioneers of the past. For centuries, eccentric aviators have dreamt of taking to the skies, building hair-raising contraptions. In the 1950s, there was a new wave of construction. Inspired by science fiction, the goal was to pare down the kit and fly like a superhero. But before all of this, the first successful personal flight took its inspiration from nature.
Yes! Woohoo!
5-time world champion hang glider Carina Schweigershausen is soaring high above the Bavarian Alps.
You see the beauty of these cliffs. It's amazing.
She's only able to fly like this because of one inspiring 19th century visionary. Engineer Otto Lilienthal was the very first birdman. In the 1870s, he began designing a range of winged machines based on his studies of the mechanics of bird flight. 2 decades later, he had constructed the first known hang glider.
Look at this. This is Otto Lilienthal with his glider. You see, it's a very simple construction, just made from some fabric and some steel wire and willow wood.
But engineered with an understanding of wing aerodynamics, in 1891, Lilienthal's glider changed aeronautical history, successfully taking to the air.
He could launch it just by running off a hill and then get airborne by playing with the wing and the angle of attack of his design, and it worked. Up to today, not only our hang gliders, but even the big passenger planes use just the very concept that he started with his wing, and it's a miracle, isn't it? The holy grail of aviation history.
Like jet suit inventor Richard Browning, Lilienthal was convinced that testing his ideas was key. Throughout the 1890s, the ambitious aviator completed over 2,000 test flights on a series of gliders.
He didn't just talk about it, he didn't just draw designs, he built them and he tried them and he proved that it's possible.
Over 5 years, Lilienthal increased his flight distance from 25 to 250 meters. He became known as the Flying Man.
In my thoughts, I often take Otto Lilienthal up to our flying adventure. I'm sure he would love it. He would love to soar with the birds, just like we do. We all owe him and adore him because he made our free flying possible. He planted the seed for the whole history of aviation.
Hidden in a secret location in the British countryside, an unconventional team of engineers are bringing Otto Lilienthal's passion for personal flight into the 21st century. Richard Browning's pioneering flight suit may not have wings, but like Lilienthal's gliders, this engineering step into the unknown relies on vast amounts of trial and error.
So our development approach is one of actually having a portfolio of different attributes to the flight equipment that we try and progress all at the same time. Some of them end up unearthing interesting opportunity, interesting revelations that we never imagined. Other ones that we thought would be easy just hit a brick wall and we'll pause.
Richard first strapped a jet engine to his arm in 2016. Then tried to take flight with one on each arm. Then two, before attaching three.
So after really learning from safe failure. So in other words, learning from trying things and often falling over and realizing those things didn't work. That methodology allowed us to learn really quite quickly.
Months of modifications with state-of-the-art equipment eventually pay off.
Can you get Dave on the fire extinguisher, please?
Small, tantalising flights show early signs that Richard Browning's fantastical dream could become reality.
It started to dawn on us that actually this is only the beginning. I think we can take this an awful lot further.
But to push on the jet suit's development and reach higher altitudes, he would need someone with his head in the clouds.
3, 2, 1.
Aeronautical engineer and world-class wingsuit base jumper Angelo Grubasic knows a thing or two about pushing the limits of human flight.
I've always been fascinated with skydiving, eventually getting into wingsuit flight, essentially trying to experience exactly what birds achieve on a daily basis.
He's tasked with refining Richard's efforts. But going from wingsuits to jet suits poses many problematic questions.
Where do we mount the jet engines? Do we mount them on the arms? Do we mount them on the back? Do we mount them on the upper arm? Do we mount them on the lower leg? Do we go on the thigh? There's been no textbook about how to approach this particular aspect of human flight.
Angelo and Richard's combined engineering expertise allows finessing and testing to step up.
Okay, Angelo, let's roll.
Hundreds of man-hours increases their altitude. Now they can fly as high as they dare. Despite some bone-crunching finales, the team have made an engineering breakthrough.
What we've done is settled on the best solution. 2 engines on each forearm and 1 larger engine on the rear. There have been several leaps forward. One of those was the angle at which we position each of the engines relative to the forearm. So actually splaying them out slightly gave a lot more stability. Moving the engines to the rear rather than the lower legs also was a huge leap forward as well. To be integrated into one of these machines is absolutely phenomenal. I like to participate in a lot of extreme sports, and this is the most extreme sport there is.
In a matter of months, the team have come a long way. But for today's Showcase Farnborough display to be a success, they must overcome a huge problem.
How do you produce enough thrust to get a human being off the ground?
Constantly defying gravity brings many challenges.
Coming up with something that was safe and controllable and in a small package, that was a major challenge.
To fly like a superhero is an impossible dream. But now, groundbreaking engineers are making science fiction reality.
For me, the freedom of flight is about not being in an aircraft, it's being the aircraft.
I mean, it sounds ludicrous, but nearly every major breakthrough in human technology has always sounded ludicrous.
At Farnborough Air Show in England, one of the most prestigious events on the international aeronautical calendar, Richard Browning and his team have been hand-picked to demonstrate their visionary innovation.
I never imagined I'd be here at Farnborough in front of huge crowds flying a 1,000 horsepower jet engine suit. It's quite a privilege.
As the world of aviation watches,
Alex, this one sounds a little funny. It's a new one.
inventor Richard Browning gears up for one of the biggest flights of his life. The jet suit's nerve center is a heads-up display providing in-flight fuel and engine status. Its range is 1,400 meters, equivalent to the length of 28 Olympic swimming pools. A 50 km/h top speed makes it the world's fastest body-controlled jet suit. But propelling a combined weight of 120 kilograms this fast requires an immense amount of force. At a secure location in southern England, lead aeronautical engineer and test pilot Angelo Grubasic is charged with solving the propulsion problem.
You essentially need to produce a lot of thrust. There are two major problems to solve. One is, how do you produce enough thrust to get a human being off the ground? And then, how do you do that in a fuel-efficient way?
For inspiration, the team looked to the engineers of the past. Gliding allowed man to soar into the skies, but relied heavily on nature. So engineers created their own propulsion.
Ooh.
In 1955, man stood above an almighty propeller on a rotor craft. But the blades proved unpredictable. A safer alternative was just round the corner. Mechanical engineer Dan Dickrell is in Niagara, upstate New York.
This facility is the Bell Aerospace Company airplane factory. It's a really impressive piece of history in terms of airplane manufacturing.
He's gained exclusive access to the site of the greatest advancement in personal flight.
It's a cool experience to be here right now.
In the 1950s, Bell Aerospace were attempting to develop a flight suit for the US military, an innovation for the soldiers of the future.
Bell challenged its engineers. How do you make a person fly?
Aeronautical engineer Wendell Moore believed rocket propulsion was the solution. In the late 50s, he developed an incredible piece of military kit. The first controllable rocket pack.
So this is it. It's the Bell rocket belt. It's pretty cool to be up close and personal to this very basic yet historic thing. This is not a model, this actually flew. Check this thing out. It's got a polystyrene and fiberglass harness. That's where the pilot goes. We see these controls. There's throttle, there's directional thrusters, the aluminum foil sort of hoses that come down. This is actually the rocket nozzles themselves. We swing around the back, we can see there's these 3 storage tanks. There's nitrogen in there and hydrogen peroxide in the 2 outer tanks.
Compressed nitrogen gas in the central chamber pushes hydrogen peroxide out of 2 surrounding tanks, bringing it into contact with a silver catalyst. This causes the hydrogen peroxide to instantly decompose into water and oxygen, sparking a huge reaction.
That hydrogen peroxide reaction is really energetic, creates a lot of heat. So that water gets turned into steam, expands to 5,000 times its volume, and exits these nozzles at over 1,000 meters per second.
This almighty force was powerful enough to lift man from Earth. Extraordinary energy created by chemistry.
So what I have here is effectively a small car that will be rocket propelled. All right, so let's draw in some hydrogen peroxide. I'm gonna add this to these silver spheres. This makes a lot of heat. We can see the reaction is happening. Oh wow, that's not a lot of hydrogen peroxide and not a lot of silver. And it is propelling the car down the table. You can see the hot gases coming out, and even though it's going slowly, it's the same premise that's used in Wendell Moore's rocket belt. We can harness the power of a chemical reaction and make all sorts of mechanical motion happen. Science.
Just like the jet suit's team of engineers, Wendell Moore used the most astonishing science of his day to launch man into the air.
Okay, I've got to get in this thing. How often am I going to be able to try on a Bell rocket belt? So squeezing into this, it's kind of a tight fit. Being in this thing, it's hard to imagine. It's hard to imagine how someone would actually fly.
But in 1961, the Bell rocket belt did just that. Propelling its pilot around 10 meters high, it reached a controlled 55 kilometers per hour. But despite impressive aerial displays, Wendell Moore's space-age invention had one major limitation.
The Bell rocket belt was not successful in the end because its thrust-to-weight ratio was just not good enough. You only had about 20 seconds of flight time in this version, and that was not practical on the battlefield. But Wendell Moore had proven that personal flight was possible. It's just that the propulsion system is what needed some tweaking.
Inventor Richard Browning and his team of engineers owe a huge debt to the early rocket men, who unknowingly ruled out the inefficient chemical power of hydrogen peroxide as a propulsion solution. Another option was the traditional rocket, burning 100% solid rocket fuel in an explosive reaction. This generates enormous thrust, but is fuel inefficient and dangerous when it comes to personal flight.
If you look at solid rocket motors, you're talking about a very difficult to control technology. Once you light that solid rocket booster, it's going and you're not stopping it.
Rocket propulsion wasn't the answer, but another technology powered by kerosene stood out. The microjet engine.
It didn't take us very long to really settle on jet engines as a very likely good solution. It's a very small, lightweight form of thrust relative to how much it produces. The power involved is enough to take that mass supersonic. And the fuel in kerosene is actually extremely energy dense, and yet at the same time not very volatile and not really that prone to explosion. It's actually pretty safe as fuels go.
What's expelled from the back of a jet engine is mainly air. In this case, ejected at 2,700 kilometers per hour. The superpowered process starts at the engine's front. Air flows in through an inlet. It's compressed, combined with kerosene fuel, and ignited, which produces a hot airflow or gas. Forced through a nozzle, it rotates a turbine, which helps ingest more air, generating immense thrust. The team have spent months developing customized jet engines or gas turbines at their secret test facility.
So this is the solution. This represents the ultimate in gas turbine technology. It spins at about 117,000 RPM, so we're looking at nearly 2,000 revolutions every second. The gas is coming out the back at over 1,700 miles per hour, at about 700 degrees Celsius. This is, in terms of brute power, the highest power density that you can get out of any particular kind of engine. To put the power of these engines into perspective, when we've got all of our engines integrated on the suit, we're producing nearly 1,000 horsepower. And if you can imagine, it's like having two Ferraris at full power acting on the human body. That's the amount of power we've got going through us. And that's all being produced by these very lightweight gas turbines, each weighing no more than 1.85 kilos.
Okay, right. Looking good?
Design engineer Sam Rogers is conducting an idle test on these small, yet remarkably powerful engineering marvels.
Yeah. It's going to spool to about 30,000 RPM, and then it's going to sit at that throttle. So already you can feel some of the thrust produced just below idle. But it's a very small amount compared to the amount of thrust you get on full throttle. You can really sense the amount of power that this unit has.
This ingenious, compact, lightweight solution radically increases flying time.
The microturbine allows us to have a high level of thrust for a much longer period of time. We're now into the minutes rather than seconds. It means we can have reasonable flight time whilst having a reasonable fuel efficiency at the same time.
In little more than a year, the team have gone from barely getting off the ground to 4-minute-long flights. Once airborne, they face another seemingly impossible problem: steering.
You're not using wings, elevators, rudder. We've got none of that. We honestly didn't have an idea of how we were going to do this.
And landing is even harder.
You don't want to drop out of the sky because you ran out of fuel.
Hampshire in southern England, at arguably the most prestigious aeronautical event in the world. 80,000 spectators and top aircraft specialists flock to Farnborough Air Show to witness the latest innovations. As part of the exclusive lineup, an audacious team of engineers are showcasing their awesome invention. The fastest body-controlled jet suit in the world is powered off the ground by 144 kilograms of thrust, produced by 5 innovative microjets, with the potential to one day fly 1,000 meters in the sky.
So we're going to come down here, we're going to stop about here.
Today, pioneering pilot Richard Browning prepares to take flight.
You're going to take off and go that way.
Yep, and you're going to go...
I'm going to go that way, probably turn around...
by the white lines.
I want to pass you in front of the stand, ideally.
Yeah.
There's enormous pressure to get today's complex flight right. Engineer Angelo Grubasic knows the challenges that lie ahead.
When you choreograph performance, there's going to be quite a large number of sharp turns that you're going to have to execute. And that demands a certain amount of control and maneuverability.
But just how do you control and steer over 1,000 horsepower strapped to your body?
You're not using wings, elevators, rudder. We've got none of that. We honestly didn't have an idea of how we were going to do this.
A solution to their seemingly impossible problem lies with the innovators of the past. But the group of engineers would have to reach for the stars. The Space Rocket Center in Huntsville, Alabama. The home of America's first space program.
Sorry, I keep drifting away from you.
Where aspiring astronauts get a taste of what it's like to maneuver at zero gravity.
I'm going to slow down here for a minute.
But one man knows how it feels for real.
When you're outside and the only thing between you and the rest of the universe is a little bitty thin sheet of Lexan that's comprising your helmet, the colors that come through, the detail that comes through, it just boggles your mind.
Veteran astronaut General Bob Stewart is one of a privileged few. He's spent almost 300 hours in space. Stewart was the first active-duty Army pilot to ever make a spaceflight.
When you're there, it's a complete sense of freedom. You can have lunch on the ceiling, you can lift huge weights, you can get on the sidewall and jump through the middle of the cabin and try to grab peanut M&Ms as you go.
However, working in space can also be a dangerous business.
This is Mission Control Houston. The hatch is now open.
Astronauts often had to conduct repairs outside the safe confines of the shuttle.
Mark, we got about 60 to go, 60 centimeters.
And were tethered to prevent them from floating away, at the cost of maneuverability.
The primary problem with being tethered in space is that restriction. I want to go out here to fix something, and my tether is 3 feet too short, and I'm sitting here so close and yet so far.
Your safety tether is going to pass your left knee. I'm trying to get on the other side. We'll go with it. We'll just keep an eye on it.
You get to thinking, what if I could figure some way to do without that tether so that I'm no longer constrained?
Yeah, that's it. And you can head toward the airlock.
In 1984, NASA engineer Charles E. Whitsett came up with a solution that would free up the astronauts and allow them to make untethered flights outside the craft. An invention that could help out the jet suit team. Known as the Manned Maneuvering Unit, or MMU.
With this machine, we could fly freely, and it is just the most delightful flying machine that I've ever encountered. It is the easiest thing I've ever operated. I told the people on the ground that I could thread a needle with this thing.
It allowed Bob Stewart and his fellow astronauts to make the first ever untethered spacewalks.
Good boy. Thank you for bringing me home.
The MMU gave astronauts complete control in this most unforgiving of environments.
If I want to roll the vehicle, I roll it with this axis right here, just with those fingertip-type motions. If I want to pitch it, it's a rotation like this. So by combinations of these movements, I can make the machine do anything I want to as far as the attitude that I'm in. If I want to go somewhere, I do that with my left hand, the translational hand controller. And it is a push in the direction you want to go type of control. This would back me up, this go forward, this slide me to the right, slide me to the left, and push me up or down.
This mind-blowing maneuverability was down to precision thrust control. 3 thrusters located on each of the suit's 8 corners were orientated at different angles, producing intricate and effortless steering. 12 kilos of nitrogen provided propulsion for a 6-hour flight.
I felt very relaxed in this thing because I had been working my butt off in the payload bay. And when I got time to fly this, I just slid back in here, and it was like sitting in an easy chair. I'm gonna go out 100 yards from the shuttle now, so there we go.
After 3 space shuttle missions, NASA retired the MMU.
It makes me sad to see that NASA made the decision to discontinue it. And about 6 of us guys went to the bar and had a beer and cried about it, because it's a lovely flying machine.
Though successful, ultimately untethered flights in space were deemed too risky. But the MMU will forever remain an icon of spaceflight.
When you reach far and you try to grasp things so far beyond your capability and you make it work, that is a great, great feeling.
Back on planet Earth, Richard Browning and his team are also directing thrust to maneuver their jet suit. But unlike the historic MMU, it's the pilot who moves or vectors the engine's nozzles to give precise control.
To our surprise, what started to bear fruit was not the idea of individually controlling the throttles of each engine. It was not vectoring them with adjustable nozzles, it was actually vectoring them using your arms. The geometry of those arm mounts is very, very specific, and suddenly it unlocked a huge amount of stability and control. It feels entirely planted.
The solution is to have 3 main points of thrust to form a stable tripod of air. All 5 engine nozzles are fixed. Those on the arms can be adjusted by simple movements, creating a stable 3-point vector control system unique to the jet suit.
So this is the solution that we've found works best, creating that 3 thrust vector control. So 1, 2, and then 3 on the rear. And between those 3, you balance all of those thrust vectors. For example, to lose altitude, you flare out the engines, which are operating at 100% all the time, and they will reduce your vertical thrust vector and you will descend. As you bring the arms in, you're increasing your vertical thrust vector and you'll start to gain altitude. And then very small changes in those thrust vectors are enough to actually initiate roll or sliding side to side. And it's all to do with weight shifting and thrust vector control.
Manoeuvring these cutting-edge jets is finessed for hours above the safety of water. Shadowing a nimble jet ski proves the perfect way to fine-tune this skillful control. But with any flight, the stakes are high. It's critical pilot Richard knows that all 5 engines are operating smoothly. Engineer Alex Wilson is facing this communication challenge.
Richard doesn't have a cockpit to sit in, he doesn't have his panels of screens in front of him, so he needs a way to be able to monitor this in real time as he's flying. When you're flying along at 30 miles an hour, 10 feet above the ground, it's quite important that you're able to monitor the amount of fuel that's left in your tank. It's quite a critical thing. You don't want to drop out of the sky because you run out of fuel.
Alex and the team's solution wouldn't look out of place in a sci-fi movie. The jet suit employs the latest engine control unit engineering. State-of-the-art electrical systems monitor and control each engine to optimize efficiency. An ultra-lightweight carbon helmet and visor with built-in display is wirelessly linked to the suit, constantly updating the pilot with engine and fuel data.
So each one of the engines that we have on the jet suit requires its own little control system to read the engine data and then report that back to a central hub. The control board is the brains of the whole system that monitors all of the 5 engines' data so that you can package this into the most important vital systems information to send up to the heads-up display so Richard can monitor his temperature, his RPM, most importantly his fuel systems, so he knows how much fuel he's got left.
So head-up display.
Oh, so this is a new one where we've taken...
Alex is continuously developing the electrical systems.
Do you want to try it on?
Yeah, let's do it.
He's currently trialling improvements to the heads-up display.
So how does it feel now?
Oh, it feels perfectly normal. It's really nice, yeah.
Mind-blowing technology first used by fighter pilots. All vital information is projected in front of the pilot's eyes.
This solution is brilliant because it's focused right at infinity, so I can stare right ahead, I can look wherever I'm flying, and then still be able to see all of my engine systems in real time without having to focus, and it just overlays it over my normal vision. Without this heads-up display, this whole venture will be so much more dangerous. It's like flying a plane without a cockpit.
But to stay at the cutting edge of new technology, the whole suit must also be developed to the max.
When working on something as advanced and futuristic as a jet suit, we need a manufacturing process that can live up to that.
And will the team's showcase flight rise to its impossible challenge?
It's happening. He's about to take off.
Farnborough in southern England. Where innovative engineers are showcasing their phenomenal jet suit at one of the world's greatest air shows.
It's pretty special every time I fly this anywhere, really, even in testing, but to do it in Farnborough, the home of British aviation, and in front of a big crowd, and on a runway where so many other amazing aircraft are flying, it's exciting and exhilarating and certainly focuses the mind.
It has taken hundreds of hours of testing to get to this stage. Throughout this 15-month process, evolving the suit has been vital. Countless design alterations have created massive challenges for design engineer Sam Rogers.
Bringing the flight suit to life really wouldn't be possible without a very reactive manufacture process. Some of the main challenges are to be able to test and iterate very, very quickly, and keeping ahead of anyone else who may be developing a similar technology is very beneficial.
In this fast-moving market, global competition is fierce. A futuristic jet board, high-speed formation-flying jet wings, and a rotary-powered jetpack are all vying to be a major player in personal flight. If the Jetsuits team are to keep ahead of the game, they need a super-fast build technique.
When working on something as advanced and futuristic as a jet suit, we need a manufacturing process that can live up to that.
Fortunately, one of history's engineers can provide the solution. In 1983, American Chuck Hull came up with stereolithography, an extraordinary layering process which focused a beam of ultraviolet light onto liquid to form solid structures.
The value to that is that you can see your design errors, you can get feedback, you can change it quickly and have another one.
Hull's innovation would evolve into what is known as 3D printing, a game-changing invention that is now allowing the jet suit's engineers to build the impossible. The starting point is selective laser sintering, or SLS, an efficient process used to prototype new parts in plastic.
We use the nylon SLS process to test fit some of the arm mounts, and then if we're happy with the fit, then we'll move over and build this in metal, because the metal process is significantly more expensive than building something in polymer.
Printing in metal involves trailblazing engineering. A computer-generated design is brought to life by layering powdered titanium in the metal sintering machine.
So in here we have the receptacle where the powder is stored. At the bottom of this there's a plunger type mechanism that will rise, and this will cause the powder level to rise at the top here. This mechanism, called the recoater arm, will then drag a layer of powder over the build plate. This very thin layer will then be scanned with the laser.
Today, the lab is prototyping some new intricate designs. The laser operates at 1,668 degrees Celsius, instantly melting each minute layer of titanium.
The layer thickness depends on the material. This can range from 20 microns to 40 microns. 20 microns is 20 thousandths of a millimeter thick.
Once melted, another fine layer of titanium powder is dragged across to repeat the process. This precision layering builds a complex design in one single structure. Detailing on this micro-turbine housing would simply not be possible with conventional manufacturing.
And that's how it would look like once it's completed. This would comprise of about 5,000 layers and probably take about 2 days to build this part.
3D printing's speed and seemingly impossible detailing are making the unlikely dream of the gravity-defying jet suit a reality.
It really makes a huge difference on top of what we would be able to do with standard manufacture methods. It really removes the limits of what we can create and design for the flight suit.
At Farnborough Air Show, Richard Browning makes final preparations for a flight that must impress the aeronautical community. If getting off the ground safely wasn't tough enough, today's routine is choreographed with the team truck.
Of course, when you've got a truck coming towards you at quite a speed, you've got to have good control and make sure that at no time do you ever even consider moving in front of that truck.
It's happening. He's about to take off.
Finally, the jet suit is launched. Propelled by 5 miniature jet engines.
Come on, Richard. Come on, Richard.
Encased in cutting-edge materials. Richard's seemingly impossible flight rockets to 30 miles per hour. It's a daredevil climax. Completed with pinpoint accuracy.
It's great. I mean, it's an amazing venue to be flying around in. Everything ran very well, felt smooth. Yeah, it's really good actually. Very pleased indeed.
The personal jet suit's successful Farnborough debut will ensure they land firmly on the world stage.
As an aerospace engineer, it's phenomenal. It's the ultimate project. To be building these systems, wearing them and flying them, it's just a dream come true.
For this ambitious aeronautical team, the sky's the limit when it comes to impossible engineering.
Being able to actually touch and hold this machinery is something that I've always really wanted to do from when I was very young, and to be able to actually get up close to it, feel it, see how it works is a real privilege.
This system is unlike any of the human flight systems we've seen before. Controlling all of the thrust, having it directly onto your arms is just so much more exciting and so much more inspiring.
By building on the work of the pioneers of the past, overcoming huge challenges, and pushing technology to even greater heights, the engineers are succeeding in making the impossible possible.
Some of the technology could well create an entirely new direction for human mobility. I think the suit opens up a doorway to an entirely new world, and I'd like to think our journey has been all about that.